Okay, so folks at home, good morning. Everybody here, good morning. Here's our three goals. One is let's briefly make a battery, analyze it, write down its redox reaction. We started yesterday, and I'll bring out the materials in my little kit for you.
Oh, also, everyone hasn't called. I saw Mr. Weldon before, and he asked me if it would be better to start 20 minutes later. Because then, people who have 1 through 5th hour and have like a 20-minute break. And I said, I don't care, but.
I don't care either.
I want that 20 minutes.
You would have.
No,
You would have to go to 4:20 instead of to 4. Or to 4:10.
Yeah, I want the extra 20 minutes.
Why? You literally have 5th off.
Yeah.
Okay,
What?
I vote that we just start right instead.
Yeah,
I
I mean,
won't delay it.
You are all worried because you got a calc clause.
I'm not worried, but we're talking about it,
It's this afternoon.
yeah.
Yeah.
Yeah,
Good
it's
luck.
our 6th hour in lunch, which really sucks.
Life is full of 6 hours, but good luck all of you. Okay, so here we go. Time for counting. So, I've got 0.5 molar copper sulfate. I'm just going to pour that in here.
Nice color.
Oh, exactly.
And it is. Copper is a nice color as iron.
Yes.
And on the other side, I've got zinc sulfate. This time it's 1 molar. And I'll pour it in. This, my stick was copper. Here my stick is zinc, I hope. Yeah. Let's see. With a lot of sticks in that. Okay, that's plenty. And now,
Where's the sulfur?
there's the problem. So, why is it, besides plain, someone else say in words, what's the problem? Why do I need a sulfur? What's the problem? It's all hooked up, but electrically, what's
Oh,
the
because
difficulty?
nothing's like traveling between them, you're not like actually connecting them.
There you go. Good. So I either need one or two things. I need a salt bridge in between these, or I need a semi-permeable cup, and that's what this is. So it will allow the ions to travel, and let's put it in there. And I hope after a moment we get a voltage.
What is the cup made of?
It's a type of porcelain that allows, once it's saturated, some of the ions to move back and forth.
It is.
No, I do not. So,
It is.
there it is. So it's now having, what's happening in the wires, if I can see it.
There's an electron current.
Electrons are moving, current is flowing. Yeah, okay, good.
Can I talk?
And we got, slowly probably, probably wrong voltage. But the voltage is close to, is that 1? Is that right on 1 with that? Let me see.
Real. Maybe like there. Can do that, right?
So 1 or a tad higher than 1 volt. So let's analyze it using the data at the back of the book. We got what? Copper and zinc, and my ions, they were sulfate, so it'd be copper. Which copper ion? 2 plus, and the zinc is also 2 plus. Okay, ready? So find in the back of your book.
So does that have the voltage that's equal to 1/220th of what's like coming out of the spectrometer?
In a sense, yeah.
And what about the current? Is there a current?
Yeah, there's a current, but I don't have that to measure there. It's not going to be a lot, certainly, some small amount of amps. And we'll see today what an ampere is. But I'm flipping, folks at home, I'm flipping to the back of our book, and it's page 569, all of the reference redux half reactions. And, yeah, that wasn't so smart, because I want to show folks at home the battery now too. So let's do this. I tell you what, Shilpa, you want to help me? Actually, no, I can get that. You want to just bring the solutions up and I can show them folks at home what I'm putting together. Okay, so folks at home, here's this. That's our battery. And I've got a semi-permeable cup instead of a salt bridge. and I've got copper in copper solution, that's on the outside. I've got zinc in zinc solution, that's on the inside of the porcelain cup. And so that is given about a little over a volt, like 1.05 volts. And that's just my solutions. I used zinc sulfate and copper sulfate to get the Cu2 plus ions and Zn2 plus ions. Okay, so help me out. What have we said? I need something on the left side that is what, and something on the right side that's what? My silly rule, Aaron? You got it. So which ingredient is going to be the higher one here? Shilpa? Cu2 plus. So let me put my finger on it. Shilpa, that's 0.34. Okay. Somebody else tell me about the other one. Where's the zinc one? The zinc, read off the voltage. So I knew I got it. No D?
-0.79.
Okay. So everybody put your hand down to -0.76. So here we go. We're going to write the positive one as is, the higher one. The higher one you write as is. So Cu2 plus 2 electrons make Cu, and the voltage, we say that's E0. The voltage of the electrochemical cell is 0.76. Is that what it was? 0.34. Sorry, I'm out to lunch. Now, the other one, what do we got to do with it? Lena?
We have to reverse it, so we also have to reverse the symbol on the volts.
Dynamite. Lena, can you help me reverse the reaction? So it'd be Zn
Zn solid,
going to
Zn2 plus 2 electrons.
dynamite. Thank you, Lena. And since you're right there, you said to make now the voltage the opposite sign, so it'll be 0.79.
0.76.
I think it's 6, isn't it? I think it's a 6. Okay, so add that up, and I should get a total of 1.1 volts. And my redox, my electrons cancel. Make sure folks at home can see this. My electrons cancel, and I got Zn plus Cu2 plus from Zn2 plus Cu. That's my redox reaction. Okay? The top one is my redox reaction. The top one is my reaction, the copper one, and the zinc is my reaction. Okay, how about Rhea? That's which one?
It's redox.
Good, reduction, okay. Because it's 2 plus to 0. This is 0 to 2 plus, so this is oxidizing. I'm just having you, I'm helping you use the words over and over so you get used to them. Really, that's what I'm doing. This whole thing is giving off energy. It's positive, so it's giving off energy. We could call it exothermic. And it's an electrochemical cell.
Hold on, how do we know it's exothermic?
Because energy would be on which side? Like, am I putting in energy or is it giving off energy?
Oh, okay, it's giving off energy.
Yeah, so it's not heated at this point, but it's electrical energy. But we still say, Noah B, that it's giving off energy because we have current flowing now. So it's an electrochemical cell. That's the fancy name for what we built. And it would have a positive voltage, a negative delta G, a K that would be greater than 1 to put everything in perspective for the AP. Noah D.
So what does it mean if something oxidizes? Zn oxidizes, does that mean giving off electrons?
Yeah, it's giving off electrons. And what would be happening to the mass of the Zn, folks? The amount of mass of the Zn over time. Shilpa. You got it, because it's becoming the ion, and the ions then float around in the solution. So Zn solid loses mass. And the Cu, everybody, will gain mass. Beautiful. And the Zn is the ode, and the Cu is the ode. So now, using any mnemonic device I taught you, can you remember it, Nobi?
The zinc's the anode.
Anode, good, because I got oxidation happening there, and
Cathode.
this is the cathode. So reduction, cathode, and anode oxidation. Beautiful, folks. Beautiful. Now, this, by the way, is E0, which means standard. My E without the 0 is 1.05 volts. How come? Why? Why? Would be,
I assume you lose some energy.
yeah, why?
on the way.
Experimentally, I went through it quickly, but it's something to do here. So your folks at home need to see this all too.
Is it maybe because it's semi-permeated and so you can't?
Louder?
It's semi-permeated, so.
No, that doesn't slow down. That's okay. It's doing what it's supposed to do. It really acts, even though it's not a salt bridge, this thing really acts like a salt bridge. So the semi-permeable cup. So it's not an experimental setup. My experimental setup is okay. Rhea, you're right, but we're somewhat close in here. But you're getting now warmer. Ha ha ha. It's something else that's measurable. Aaron?
I was just gonna say it might just lose some currents between the, like when it goes around in circles.
No, that's okay. It's a complete circuit. It's all right. So Shilpa,
The concentration.
yeah, could you make a little sentence?
Standard voltage is 1-to-1 mole ratio.
All right, 1 molar solutions. Look at what I got. I got 1 molar, that's the zinc. All right. Ooh, that's 0.5 molar. So look at now, Quinn, the 0.5 molar is this one. And what's the effect of having less than 1 molar, Quinn?
There's fewer places for the electrons to go to become, like, be absorbed by copper atoms.
Good. Also talk to me about number of particles, Quinn, like Le Chatelet's principle.
They're the copper atoms are more spread out.
So if I'm doing what with the concentration? Think of it that way.
You're having the concentration means
The effect on the reaction will be to
the
shift
reverse
which way.
reaction is favored,
There you go.
and yeah, less copper is produced.
Okay, good.
There's
That-
less energy.
That's it. So what I want all of you to be able to do, what I was doing with Quinn, is use Le Chatelet's principle for this. Assume you're starting at 1 molar, and then do what I did with Quinn. Now imagine going to 0.5. So suddenly, if I have less here, I'll shift the reaction towards the side that has less. Remember how that works? It's like I'm making a hole. So it's going to shift this way. Therefore, it's going to make less product. Therefore, my actual voltage is lower. So this is due to 0.5 molar Cu2 plus, causing shift to reactants, well, a bit, which the voltage. Just so I know you're following, could somebody fill in the blank? So that shift, that bit of a shift to the reactants, the voltage, and Shilpa, thank you. Do you see how I'm trying with you to put together lots of ideas from different chapters? That's what the test will be like also. So try and connect those little parts of your brain, all right? Nodi.
I have a quick question about Chatelet's principle.
Yeah.
The whole idea of like shifting to the left or to the right, is that referring to the temporary shift to balance it? Because at some point it returns to equilibrium. Right.
Well, but it's not going to be the same concentrations as before the stress. Remember what happens is, remember Cheryl's little book, we give some sort of stress, and that stress causes the little arrows to do something. In this case, we had an arrow that will then go a little more in the reactant direction, reverse instead of forward. What that does is once I reestablish equilibrium, which I will, Noah, I'll have the numbers shifted a little bit. The equilibrium K number, if I divided those, would be the same thing. But my numbers that I'm putting in would be a little bit different. I would have a little less of this because we've shifted back to this a bit more.
Okay.
Yeah. So think of that Sherry idea of causing a stress and seeing what the reaction does to try and compensate for that stress partially.
So the shift is referring to what?
The shift is this. Imagine we were at 1 molar and suddenly I make it 0.5 molar. So it's an imaginary shift because all I got is 0.5 molar. But I find that if we do that and start with something we know, it's easier to think about Le Chatelier's principle. Okay? Rhea.
I had a question to the actual battery you made. I'm a bit confused because last time you said the salt bridge replaces the negative and positive ions.
Right.
But that's not, how's that happening in this one if we don't have the salt bridge?
Now what actually can go through a little bit through the porcelain cup?
Oh, the other ones. So.
Yeah, the actual ions. So some of the positive negatives are going through the semi-permeable cup to directly replace ones that get lost. Like if I have some that are Cu2 pluses, Rhea, that are becoming solid, and so I have less pluses there, then some of the Zn2 pluses will sneak through and then replace those. A disadvantage is I start to get my solutions all kind of messed up, you know what I mean, over time. So I wouldn't use this as a real setup. I'd use a bridge if I had one, but I don't have one that works well with this system. So I use this because it's easy to show to students. Okie dokie. I'm going to take those out. Let my little battery rest a bit. And just as a reminder, delta G would be negative here. NK would be greater than 1 because I've got a positive voltage. That's how I know all that. Right? Jute, any other last questions about analyzing a battery using the vocabulary? You guys did pretty good. This hour, I want to finish up chapter 8, and then we'll take some questions with the time remaining we have next period, okay? So where we left off was section 8.4, and more or less I think we're done with it because you've now done it physically and figured out some voltages. Let me go back and just verify that with Sherry. Yes, you've done that. Yes, you've done that. Oh, one last thing we can do. Let's do this for grins, okay? Let's do the cell notation. Cell notation, recall from last time, it's the anode, cathode. You like the special effect? I'll do it again in a second. Okay, so anode, give me from the anode. Give me from the anode reaction, what are the two main ingredients? So find what reaction's happening at the anode, look up above here. Remember how I had you remember it. And what are my two players here? Shilpa?
Would it be Zn and Zn2 plus?
Super. So here's how we write that. Zn is going to Zn2 plus at the anode, double lines. Whoop, whoop. And now somebody else do me the main reactants on the other side. Go ahead.
Copper 2 plus and then copper.
Thank you. And there you have it in cell notation too, for grams, huh? Okay. Okay.
I think you did it wrong a few times yesterday. What did you do wrong about it? What mistake did you make
We
during
didn't
cell
do
notation?
the sound effect.
Okay.
Yesterday? Oh, I put the cell notation up.
Yes.
I guessed as to what it was with that other cell I made up in my head without thinking about it ahead of time. And you know what happens when you don't think? You do stupid things. We all do that because we're human. All right, every day. Don't rub it in. Okay, here we go.
That's not what I meant, but
I know, Tuesday. See, I made another mistake without even trying. Okay, here we go. You need some equations, and we're not really going to use them much. Actually, that one we won't use at all because you don't need the Nernst. But you do need this one. I think you need this one. Let's find out. Okay, so useful equation. Pop this in your notes. So the voltage, the E0 of an electrochemical cell, and by the way, another name for an electrochemical cell is a battery. Right? Okay, so here we go. So I don't really like this so much, but we'll do it this way. How does she write it? 0.0592 divided by N times log of K. This is an equation to allow you to get back and forth between voltage and the equilibrium constant. Okay, so to get back and forth from K, but how do you do it? Well, some form of this should be on the given information sheet. I don't think you have to memorize that number. Okay, so you can look on there and see the sheet I emailed it to you to another time. But what you do know is, you need to know is N. N is the number of moles. Well, what's important once I had that battery going? Can you guess? Number of moles of what? Sure, take a guess. No, me?
Like the 0.5 mole one?
No, it's not either of the chemicals. It's the number of moles of electrons transferred. Example, in our battery, how many moles of electrons were transferred in our battery? If you look back up at our balancing, Tom? No, how many moles of electrons? Just look at the reactions. Look at the two reactions. How many moles of electrons are in there?
I have no idea. Is it something I have to look at period?
No, you just look at the freaking equation. How many moles of electrons, Tom?
What?
2.
Oh.
Me from Byron and T-Con, what the hell?
I had it covered.
I'm sorry, Tom, but I mean, 2. Okay, so 2 for our copper, zinc battery. All right. So we can just throw that in already. Check this out. E0 for the cell was 1.1 volts equals 0.0592 divided by 2 moles of electrons times log K. And let's go solve that sucker. So we got log K equals 1.1 times 2 divided by 0.0592. And what do I do to undo log, people? How can I get K? What's the opposite, like power thingy, Aaron?
No,
No.
Aaron.
Careful.
It's not the natural light.
I think it's just the log.
Don't steal it.
10 to the X power. I know what you're thinking, and there is a version somewhere, there's a version of it, Aaron, with natural log. You can look on the given information and see if they give you the natural log one, in which case you would E it, or this one, in which case you 10 to the exit. Exit?
You had it.
Just 10 it?
Yeah.
Okay. That sounds like a philosophical meaning or something, 10 it. Okay, so could you guys 10 it and see what you get? What'd you get, Shilpa?
I got 1.45 times 10 to the power 37.
Is that greater than 1?
Yeah.
Okay, so it very much favors the products, doesn't it? Okay, so that's a really big cake, but so be it. and some of them are. All right, cool, huh? Yeah, Noah?
The given information sheet that you shared on Google Classroom.
Yeah.
Like, we can't open it, we don't have the rights to.
Frickin' A, really? Okay, I'll try and give you the rights or put a different version on there. That's annoying when it does that. Okay, my apologies.
You have it, and then share it.
Yeah, I also have frankly a copy, paper copy. Maybe during break, I'll just like Xerox you one in an old fashioned way and give you a copy of it. That might be one way to do it. No, B?
So I asked you to unlock some quizzes and you did.
Yeah.
For the multiple choice, they automatically score it. But if we were to do some practice FLQs, would you be willing to score them?
I would. So if you do practice FRQs while you're practicing, just send them to me. Even over the weekend, I'll try and remember to look and score them for you. Okay? I'll try and do that for you because I know it's important you're studying.
For those practice, they won't like go into our grade.
No.
So we can mess them up.
Absolutely. You may mess them up.
Okay, fine.
You don't have to mess them up, Ray, on purpose. You could get them right. That'd be cool too. But it won't affect your grade one way or the other.
Will it affect your grade if we go really, really well?
It would be affect your grade nicely if you do well on the clausura. I'd like all of you to do well on the clausura. That has, oddly enough, a positive effect. Good. Okay, and Shilpa.
Is there anyone who practice like sample answers that would score if I like perfect answers for the FRQ practice?
Oh, boy. I have some, but I don't have anything digitally, like some student answers. No, I would just say read what they have if you can get to it, and or if you want me to grade some, I can do that for you too. Yeah, I don't have that. I will run some when we practice some other ones, but I don't have any. They're all just sheets that I have. Rhea.
Yeah, for the calc exam, I actually looked up college, I Googled the FRQs from different years, and I did them, and then I looked up what they had as the perfect answer, and then you can check how many points you would have gotten. I think that was really helpful.
Good. If you want to share that with others, some of that sites and stuff, please do so. That'd be great.
There's also a really good scoring site, I forget what it's called, where you like, you put in, I used it for the SAT, where you put in your score and it tells you what, like, 1 to 5 scale grade you would
Oh, yeah, I saw that.
I forget what, Albert.io or something, is it what I don't know, it was really funny. But it was like really good and it was pretty accurate.
Okay, so thank you for sharing that and help each other with that. Share that on the chat or whatever chat you guys are using. That would be terrific. And I'll try and help you with some grading of things too. Now, here's the unfortunate, confusing part, and this is the end of some of chapter 5 ideas, and it's this. There's 2 phrases that sound really similar, but they're not the same thing. In fact, they're opposites.
We've had this before.
Good, then you can tell it to me.
Not like we've had that opposite phrases that sound similar before.
Yeah? We're in English class or something?
And that's about
Entropy
entropy.
and entropy.
Oh, what then? Okay, all right. They're not that
They're so
similar. Okay,
similar.
all right, okay. So, but enthalpy and entropy aren't exactly opposites. Well, anyway, okay, so here we go.
You
So
literally taught us about that.
Judge-
electrochemical cell, common name battery. It's
That is a story.
exothermic. It's got a positive voltage,
Saying that.
negative delta G, and it's got a K greater than 1. Electrolytic cell. The process is called electrolysis. These suckers are endothermic. They have a negative voltage. They have a positive delta G, and they got K that's less than 1. So they're not spontaneous, but they're important. Especially they're the main one used in industry. So all of this means to make electrochemical cells work, what do you suppose you got to put in if this is your industry to make those cells work? Yeah, money, but directly put in
Energy?
Energy. Okay, so all of these require that you put in energy. So energy, and I'm talking electrical energy, you got to put in a lot of electricity. So you got to put in electric current to make these run. And I'm sorry the names are so similar. So if it's electrolytic cell, that requires energy. And we're going to look at one right now.
Sorry, this can only stick wires in a bucket of water.
Essentially, that is one, yeah. If I electrify water, electrolysis of water, or hydrolysis, it's a special name for water, that's an electrolytic cell, exactly, Glenn. And don't put your finger in the water as you're doing, okay?
And don't like hold a match over the water.
A match over the water. Well, I'm not sure how effective that would be.
I would cause. It would cause an explosion though.
Oh, you mean while it's running? I
Yeah.
thought you meant to get it going.
Oh,
Okay,
well, yeah, don't do it while it's running.
okay, yeah, agreed. Huge. Okay, so the main purpose of this industrially of electrolytic cells is to plate metal out. And get metal from metallic ores. And I'm talking basics we use for our society. Iron, aluminum, all the stuff we use to build things.
I think melted iron. Okay.
No, to plate out metal, yeah.
Plate.
And
Pipe.
yeah, to plate out, that's what we say. I'll tell you in a second.
I
And to
can
get
do it for
metal-
aluminum, but
Out of
iron, you just melt the ore. pretty much.
metallic ore. Now, iron, you gotta get it out of the ore. So that would be like going Fe2O3, and eventually you get Fe out of it. But it doesn't happen by magic. You gotta put in a lot of electricity. By plating out, here's what I mean, okay? If I take a key and make my key out of whatever, iron or whatever, doesn't matter. The outside of the key has a different metal on it, and it's a metal that's very resistant to abrasion. What they do is they drop the key into a solution. Here's the key. And this solution has, let's say, chromium in it. I'll just make something up, 2+ or whatever, okay? What happens is if they put in electricity, so they put in electricity, we electroplate the key. Electroplating means I'm adding another metal on top of it, on top of the one that's there. So it's a process of putting another layer that wouldn't naturally be there, and I've got to do that electrically. It won't happen on its own. I got to put electrical current through the solution. So it's often called plating out. Imagine that your key is the plate, and I'm getting metal out of the solution. That's maybe a way to think of it, plating it out.
Still don't understand how you do that for iron.
I'm not doing it for iron. Iron is another process. So you can plate out, that's over here, Quinn. But this process is something different. It's getting some sort of metal out of the ore, out of the ground. Like this is an ion, and I've got to change it to iron metal.
You don't need electricity to do that. You just melt the ore, I thought.
No. Iron really likes oxygen. You can't just melt it. They won't like go apart. They're pretty good friends. So you got to put in electricity to convince the iron to grab a couple of electrons and become iron metal. It doesn't really want to do it. That's why rust is really common. And chunks of iron are less common to find in nature. But there's lots of rust out there. Ute. Let me think of the best way to do one of these. I think I'm going to jump to the chase and just go to the last section. So 8.6. And 8.6 has to do with how much, in terms of grams, can I make with electrolytic cells?
One question, what does it mean to plate out metal?
Well, I've been trying to explain that. Plate out is the word to make something go onto another piece of metal or plate. And so it comes out of the solution, the ions. Like let's say my metal I want to have on the outside of this key is chromium. Then I make the chromium ions by using electricity, grab onto the key and coat it in a nice smooth way. So essentially I'm making more chromium metal out of it.
And
So plate out means to go from ion to solid.
And electricity is giving them the electrons that they need to become solid.
Yeah, and it's forcing the reaction to happen. Because remember, to be spontaneous, Noah, we've always had one above here on the left side and one below, right? Well, guess what? This chapter is like this. So the only way to make it happen is I got to put in electricity to force stuff to run the other way. Yeah. Go ahead.
I looked it up, and like this makes sense historically. You do not need electricity to smelt iron because, like, way back when in the Iron Age, they had no reliable access to electricity.
And they did
Therefore,
not but melt it.
Yeah, you were
Okay.
able to break down hematite by melting.
Okay, I stand corrected. So look up the same thing with aluminum.
Yeah, it is. Like, have you seen how thick the electrical cables
Look
are?
up the same thing with aluminum.
Yeah, I know. I know
Okay,
how, like,
so my point is, okay, if I'm wrong about iron, fine, but believe me, this is how we get most metals. Okay, so if it's not iron, thank you, Quint, that's fine. But to get metals, we got to electroplate out a lot of them to get a useful coating on materials that we use as a society. So here we go. We're going to do this sucker. So it's using a lot of stuff you haven't had yet. And it kind of goes like this. We need Faraday's constant. This is given on your given information sheet, which I'll try and help you get and open it up for you. Faraday's constant, 96,500 coulombs is, why does that not sound right? Maybe that's right. Is 1 mole of electrons. So coulomb is an amount of charge, okay? An ampere is a measure of current. So this you might have had in physics, but if you haven't, then you're going to get it slapdash now. So 1 ampere, or amp, as they say, is 1 coulomb per second. We got to give you that equation too. I might as well give you this equation too. To get the delta G, I should have done this when we did the K. To get delta G, here's the relationship. Delta G, the standard one, is equal to minus the number of moles of electrons again. This time the N is still moles of electrons, times Faraday's constant, times the voltage of the cell, the standard voltage of the cell.
did the whole metal cage thing.
That's the same guy, yeah, Michael Faraday. So N is still the number of moles of electrons transferred. And so F is, yeah, the F is this, 96,500 coulombs per mole of electrons, okay? Now, it's got to be not negative because, for example, if I had a battery, I'd have a positive voltage, but that would make the delta G negative, like they got opposite signs. That's why there's a negative in there, okay? Okay. You can use that. What happened? Okay, I'm still there. You can use that at your leisure, but I've got a more important question type to do with you. Okay, so let's get to one we can do. Whoops, ran out of book. That's not what I want. I want to come back and do one that maybe she did. Okay, here we go. All right, so come back, teacher. What mass of what mass of nickel, solid nickel, can be deposited or plated out I'll write it as she does, on a graphite cathode. It doesn't matter what it's made of. In this case, it's graphite. By using 15 amperes and 2.2 hours in a nickel CO2 solution. Hold on just a sec before you go. And we've got to assume that that's 1 molar. She should have said that. Good. We'll do that when you come back. Question mark. Good. Let's see if I can give you permission on.
Can I give my chapters?
No, I'm going to grade all the books after the clausura, but I don't want to grade it now because I need to do this more importantly for you to get you that given information sheet. But if you're caught up and working hard, Lena, I'm happy. And I know you are. Okay, so let's go to Google Classroom and give you this permission.
You're not using no first, I was like, there's some things I'm like, you know, like, that's what the rest of it was like.
Okay, you should now have permission, everybody at home, to look at the given information sheets that I sent you for the clausura. You'll get a copy just like it for the clausura and a copy just like it for the actual AP test in May. Okay, so let's do it. By the way, I looked this up. You actually don't need the concentration, so I'll put a line through it. You just need the presence of the ions, as it turns out.
You just need enough ions.
Yeah. Okay, so what mass? So we're going for grams. And what quantity you suppose we're going to start with? What quantity will we start with? Tom, if you could put it away, that would be most appreciated.
Well, I mean, we're solving for mass, so I assume we have to try to find the number of moles and convert that to grams.
Again, yeah, so, but look at what we're given. We're only given, what number could we start with that's given in the problem? What quantity?
We have Faraday's constant, and we have that it's 15 amperes. So,
And we got 2 hours. Again, my question, which number do we start with? Because we're going to make a little plan. And I know this is tough. Which number do we start with to start our calculation? You got a guess, maybe?
I would think 15 amperes?
No.
Oh, wow.
Ampere is coulomb per second. So in chemistry, you almost never start with like a double label. What's a quantity we have? Well, the only one left is Rhea. Which quantity?
2.2 hours.
Yeah, so we're going to go hours
Thank you.
to seconds. And then check at the top board out. I can go from seconds to what? What new quality do we have? Seconds, I can go, Aaron, to coulombs first. Coulombs. So I can go from seconds to coulombs. And then I can go using the amperes. Using the amperes, I can go to what?
moles.
Moles. Moles of what? Tom? Electrons. Because if you look up here, I know this is new for you. It's coulombs to 1 mole of electrons. So we're going to use Faraday's number to help us get that. Then I can go from moles of electron to moles of in this case, what? Moles of electrons to Shilpa, moles of nickel. And then, as Noah D, you said earlier, then we'll go to grams of it. And that's the last step. Okay, that's quite a plan. Okay, so I want you to just think about that. So the quantity you end up starting with often is the time. So let's do it. 2.2 hours times, and look at this, 1, 2, 3, 4, 5 flipping arrows. 1, 2, 3, 4, 5 conversions. Whew. Here we go. So we got arrows, we got hours to seconds. What number would that be, Shilpa?
3,600.
Thank you. So every hour is 3,600 seconds, so now my hours is gone. And I'm going seconds to coulombs. I can put in what here for that. Look at the data, look at the numbers up above. Nodi?
The 1 ampere, so 1 coulomb over 1 second.
Yeah, I think that's it. So I can do, but it's not 1 ampere. It's how many amperes in this case, Noah?
15.
15. Coulombs per second. Now, what's the next thing? Quinn, what do I got to do here?
You divide by 96,500 coulombs per mole of electrons.
Thank you. And now I got to stop and ask you, boop, back from the first couple of weeks, what's the charge on nickel as an ion? The charge of nickel? We'll have to know that here. Aaron? 2+, right. So I'll need to get a mole of solid, Aaron, I'll need how many moles of electrons? 2. So just to write that out so I don't lose anybody. So I need another factor to do that, okay? So for every 2 moles of electrons, I get 1 mole of Ni. So you can't forget that little tiny step, or else you get like off by a factor of 2, which is a lot. Good. Then look up the molar mass of nickel, somebody for me. I don't remember what it is off the top of my head.
58.69.
Thank you. Could everybody punch all that out on your calculators, and I'll do a little walk around the room and meet and compare notes here. Compare answers.
So nice when the unit sounds fun.
Okay. What did you get? No B, what'd you get?
I got 36 because we need 2
Good. 36,
grams.
oh, I forgot my label. Gosh. Others, let's see if you get the same thing.
Yeah, 36.13, yeah.
Thank you very much for doing that. So not a lot, but that's what you get, 36 grams. Yeah, what would that be, the weight of a euro, or a couple of euros? Not much. Questions from you on that? That's a lot of new stuff to digest. And again, in chapter 8, I assigned just enough to kind of get your feet wet and enough so you have a little bit of experience. Yeah.
So in AP Calc,
Yeah.
when we do free response, we can get like partial credit. How would you get partial credit on this? Like, could you get
Here's
partial
how.
credit?
If it's worth 2 points, sometimes on the AP, they might give a point just for having the students get up to, let's say, the moles of electrons. And then a second point for getting the moles of nickel, even though it's in the same problem. It's a little random to me, but sometimes they will give partial credit like that, and other times they won't. And you'll just get the points, 2 points or not, or 1 point or not. Some are just worth 1 point. Good question. Sometimes there is an intermediate step though, and they do give you a point for that intermediate step there. Last thing to tell you from chapter 8. You ready? Woo-hoo. It's just a review, but it kind of puts the course together, at least the last few chapters. Let's put these suckers together in our notes. So if I got the delta G of a cell, the delta G of a cell, I can go back and forth between this and the E or voltage of a cell by using this sucker. So the delta G 0 equals negative N F and voltage of the cell, E0 of the cell, or electrochemical potential of the cell. And I can go back and forth delta G to K by the one we used a little bit ago. So delta G0 equals the negative, oh no, we didn't use this one, negative RT natural log of K. Oh, that's kind of nice. So you could use E for that one, Aaron, to undo that one at the very end, to go between K and delta G. Now here's the one that's regular log, the one at the bottom. Okay, so the regular one is E sub 0 of the cell equals the 0.0592 divided by N times the log of K. In other words, that triangle, the equations will be given to you. I think all three of them are. But if you logistically understand that, no matter what they give you on a free response question, you can get the other thing from it. And really, this is kind of all of them built for a free response question, more than multiple choice. Okay? You're done with book 2.
Pivnerd is also tends to be an FFQ question, right?
A part of one, right? Part of one. Okay, so take a deep breath.
We're contemplating.
What questions do you have? And I mean, not just here, but are there other now, as you're working feverishly, I know, other book questions, review questions? Let's use our remaining time this period to answer your questions. When you run out, I have things I can do then also to practice with you. Okay? Shobha.
I don't have a specific question, but could you possibly just quickly go over a general idea of the equilibrium and like favoring the sides when like pressures change? Or...
Absolutely. Let's do one like that. Okay, so
We argue with
I'm gonna call it shifting.
and we spell it wrong, do we get points?
no, you do not.
Do we get generally points?
Lashada is
Is there an accent review?
yeah. If you put the accent wrong on it, you automatically get like a 1 on the tits, Gerald. Just kidding. And shifting reaction direction.
I took both.
Oh, okay. I took Latin for some reason.
By the way, before I forget too, on the clausura on Monday, here's what I did to change it. So I want to have a little shorter for you. So for one thing, instead of 60 questions, it's only 50 multiple choice questions. That's an hour and a half time. And for the other hour and a half time, you're going to have, instead of 3 long questions and 4 short, I think I gave you 3 long and 2 short. Okay, so you'll have 1, 2, 3 long questions. Then I think I gave you 4 and 6 for the short questions. So you don't have 5 or 7. So I crossed out 2 of them
So we have 3 long questions
and 2 short,
for 90 minutes.
which should give you a little extra time too. Not a lot, but a little bit of extra time because I cut 2 whole short questions.
Do we get all the breaks between hours to work, like on the vessel?
No, you 90 minutes, you don't have time for a break. 90 minutes and then you'll get a break of 7 minutes or whatever, and then 90 minutes. If you got to run to the toilet or something, that's fine.
I mean, like, do we get the breaks on top of the break on top of the 90 minutes to continue working on the exam because between, like, within the first section in the 90 minutes, there's a 7-minute break. So do we get that time to work as well?
Oh, yes, of course.
Okay.
Yeah, so I'll give you, once we start, bing, you got 90 minutes on the clock. And then when the 90 minutes are up, I'll let you know, I'll collect your test, and then you got a break. And as soon as we're all ready, then we'll take a breath and do the next 90 minutes, boom, and I'll have a specific time to finish for that too, okay? And I'll try and have some kind of clock here. Do we have any clock in this room at all? That sucks. Jesus, this school, at one point, the Ryan was gonna put them all in, of course, then they all like slowly died. But
Let's project the
I've been
time.
here too long. I could project the time. I could just put it big on the laptop. I might do that and just have the time giant here. How would that work? Silly, but I can probably do that.
We start with multiple choice, right?
Yeah, multiple choice first. Ute, we're gonna do this question that Shilpa asked about, and I got distracted with myself. I hate it when that happens. Okay. I want to pick a fun equation for this. Oh, yeah. Good. Okay, so I'll try and write it like an FRQ. Ready?
Consider the following.
Yeah, consider the following. If temperature is increased, reaction shifts to which direction? And why? Part B. If pressure is increased, reaction shifts to which direction and why? And C. If the partial pressure of NO increases, reaction will shift to which and why. Okay, try and in your head get an answer to all 3. I'll shift this so my folks at home can actually see the problem. So they're all gases. 2 NOCl gas forms 2 NO gas plus 1 CO2 gas.
Are they in a rigid container?
Yes. Nicely added. And first one, temperature's increased, which way does it shift and why? Second, pressure increased, which shift and why? And pressure of NO increases, which way does it shift and why? Okay, I'll take a walk and you think.
Wait, is pressure and
See that?
and for C, pressure and
Exactly.
But we aren't told if it's exo or endothermic.
Yeah, but you should be able to figure it out. Look at the reaction, and figure out if it's exo or endo. Use your best judgment.
Well, it's the decomposition.
So, what's your answer based on? Look at that long lost piece of cake. There, maybe. Okay, so how about Rhea? If the temperature increases, which way will this sucker shift?
I was thinking it was exothermic, but I really don't know. Would it be exothermic or endothermic?
I thought it would be endothermic.
Why would it be endothermic? Aaron,
Well, we have a decomposition, the thing is together, it doesn't really wanna decompose, so you have to like put it energy to make it decompose. I mean,
Well, it requires energy to break bonds,
Doesn't really want
and because it's a decomposition reaction.
and it needs energy to reform the bonds as well.
so if I break up one into two parts, generally it's going to be endothermic. So it's a decomposition, nicely seen, and it's going to be a positive delta H. By the way, that might be a part A. You know, is it endo or exothermic and why? So if you can explain that, that's good. But clearly it's going to be a decomposition. I'd have to put heat in. And now back to Rhea. So I increase the temperature. How will this sucker shift now?
If it's endothermic, I'd say it shifts to the right,
Yeah, which is to the products or reactants.
product.
What can we say is a reason, folks? There's several different ways you could describe to get points for this. No?
Since to form the products, you need heat, so if there's more heat, then you can form more products.
I'm going to add one thing to your sentence, Noah, or have you add one thing. So since more heat in a forms more product. In a, exactly. And I'd add that in there. So since more heat in an endothermic reaction forms more product. Good. All right, and pressure. Good.
If we shift to the left, I think have less particles, like overall, would it
I
shift?
can't hear squat with the basketball, sorry. One more time, Aaron.
Would it shift toward the reactant side because there's less, particles?
Yes. And let's add one word, Aaron, to your discussion. Towards the reactants, can't spell that. Since there's less particles of on this side, phase, what phase?
Gas.
Gas. It sounds obvious, but I mean, if I had, to be honest, Aaron, if I had 2 and 2, and if this last one was a solid, it wouldn't really matter. that weird? So it has to be a difference in number of moles of gas on each side. 2 and 2, there would be then no shift whatsoever.
Aqueous.
Would this
Sure.
be the same explanation as looking at the disorder that you're saying? Or would that not be?
It's more about space, and that's why I like Aaron's talk about less particles. So if I increase the pressure, generally they make up less moles of particles because that shifts to reduce that stress of a higher pressure and reduces the pressure a little bit. Aaron,
Liquids would also be inconsequential, right?
Correct. yeah, correct. Only gases count here for this question. Is that your question?
Yeah, mine was just about, things in an aqueous state, but I assume.
They don't do anything either. Good. Okay, Quinn, I'm gonna increase the amount of NO gas. What's gonna happen?
Well, the other side's they're going to make more NOCl to compensate, so there's gonna be less CL.
Good. So we shift towards, say it as reactants or products, Quinn?
Shift toward reactants, that means the excess NO reacts, meaning less CL.
I'll write the other thing you said too. So more NOCl is formed and less Cl2 is present. Or you could say the pressure increases and the pressure of Cl2 goes down. You could say it that way too. Okay, Shilpa, does that help ring some bells with how we use that?
Yeah. Thank you.
Good. Questions from others too. Lena?
I just wanted to make sure that I understand. So if you were to add a catalyst, it would increase the forward and reverse reaction rates at the same rate, so it wouldn't
Correct.
change anything.
Exactly. Your equilibrium not shift. Both sides would increase in rate equal. Good. And good answer to your own question.
Would that last answer get full points? Because did we explain why? Like, did we answer why?
Oh, boy. Good, Rhea. Let's see if we did. So if the pressure of NO increases, shifts towards reactants. No, I got sidelined in talking to Quinn, and I'm not blaming Quinn, but or maybe I'll blame Quinn just for the heck of it. And because of Quinn's distraction, just kidding, Quinn. We didn't really answer the why. So let's answer the why now. So Rhea helped me do that. So if I increase those particles, what happens? What could you say?
I mean, it shifts to get rid of them again.
Yeah,
So, I mean, because there's more more moles there, they react more often.
good.
So
I like that. So more NO particles then react more often. Law of possibilities to form more.
NOC.
And I think that'd be adequate as a discussion there because you talked about number of particles and what that means. Thank you, Rhea. Other questions, comments about this review question? Good. What else would you like to review, ask about, anything? Aaron?
I know this is a while back, but could we maybe just quickly review the geometric, like the geometry?
The Vesper
of
stuff?
atoms?
The geometry of something. Absolutely. It's important. Let's do a couple. Okay, so great idea. And everybody should review their molecular shapes. There'll be probably a multiple choice question, maybe even part of an FRQ about it. Let me dream something up, the question, Tom? Absolutely, please. And question, yeah, Shilpa. Yeah. Okay, so let's go ahead and do a couple of molecules. Actually, I don't want nitrogen because it's a bad boy. Let's do somebody more friendly.
The rest of the next hour off. Reduction.
I need to study the really simple stuff, because that's what messes me up, like doing the simple
Just the
Root of
motivation.
X squared.
right?
What's the root of X?
What?
What's the root of X?
What?
No.
I've been struggling with that, I would be scared.
Well, I was
No, but I know, like, my mistakes on the last test, really sure it always like just really dumb mistakes, like not doing the one over equation.
Yeah,
I
same.
don't know. Like,
You
really
remember
dumb
the
mistakes.
Well, don't do that.
The z,
Thanks.
the integral something.
Guess what my mistake was? I
What
thought
one
the problem,
mistake?
I thought the problem was done, and then I just stopped.
I forgot to
forgot to
subtract
grade
my
one of my
2, and then I didn't
questions.
write it
I'm not
down.
kidding, on the last test, I forgot to grade it.
Yell at him.
I just only got to grade one of my FFT questions. It was right, but like.
Okay, here we go. Let's try 3 of them to renew this in our heads a little bit. Here we go. So let's say I give NH4 plus, PLC, PCl5, and CO2. So try and do a Lewis structure for each. Remember how to do the hybridization of the central atom. And don't do the middle one because you don't need dehybridization. Skip the middle one for that. And then the last try and do a molecular geometry name for each one. A shape that you do.
The whole idea of hybridization, I did a bit of research on it, there's a lot of controversy
Yes.
surrounding it.
That's why they only go up to SP3 now. They don't go any higher Ds and stuff.
So why do they have those options on the AP exam? Like they had like D options on at least exams of previous years.
Because they used to have it on there until like a couple of years ago.
Okay.
And I think Sherry got on board and because of the controversy, she made them take it off. I thought our author, our hero,
The chemistry geek.
Show yourself.
Sherry the awesome. She told him what to do with it. No. So folks at home can try those too. This is really the shape.
By hybridization, I always mean the central atom line.
That's correct. And if you can do all that, maybe you can do sigma and pi bonds too for those.
Thanks.
Does hybridization only consider bonding points or
Bonds and
but like double
And-
bonds?
any unshared pairs around the central atom.
Do double bonds count the same as single bonds?
Yeah. Okay, I don't want to run out of time. Let's go ahead and do them. So how about Lena, the first one, NH4 plus, what's it looking like if I draw a Lewis structure?
You have the N in the middle surrounded by 4 hydrogens.
Good. And how do I show the plus?
You do the square bracket. And
Yep. And then,
the plus.
beautiful, good. The hybridization of the central atom. Okay, no D?
SP3.
So it's 4 things around it, so it's called SP3 to make those 4 things. What about the molecular geometry? How about Noah B? I got 4 things around one thing.
Is it like tetrahedral?
Yeah.
Plane?
Good. Now going way back, how many sigma, how many pi bonds in this one? You're in.
4 sigma bonds.
And that's it, you got it. There's no double or triple bonds, so it's just 4 sigma bonds. Ute, PCl5, Rhea.
That's just a P and then connected with 5 CLs with single bonds.
We'll skip the hybridization and the geometry. What'd you come up with, Rhea, for that?
I always forget how it's trigonal, I think. Sorry, trigonal.
Is
That's how
that,
you use it.
is that like when you have a triangle and then you have like a sigma?
Well,
So trigonal bipyramid, or you could say triangular bipyramid. I've seen that too. But I think your book uses trigonal.
You're here,
Like a,
then central out of here,
Or-
two of them, and
like
then
this?
triangle here. So triangle, and then.
You know,
so whatever you do.
So it'd be like this. Here's your P. Here's your CL above, and one below, and one at each of the three corners of a triangle like that. So it makes like a triangular pyramid above and another one below.
On the AP, he didn't have a name, but we can draw the shape like a partial credit.
damn it. We're really going for the partial.
Yeah. Because I feel like, at least like conceptually, you know,
You're gonna know most of the names. You guys are a strong crew. Just read through the names once in your book one, and you'll remember. Again, I have a lot of confidence in this crew. Okay, you're gonna know. There's not that many. There's a couple weird ones, but a lot of them are pretty straightforward ones that you know. Okay, and this one has sigma bonds, everybody. Thank you. Okay, the last one you probably have memorized after this many years. So, Tom, CO2 looks like what? Yeah.
So, it's zero. It's double bond, is it?
Yeah, exactly, Tom. That's probably a good one to memorize. And then if I had to, I got a little sloppy here, didn't I? Shame on me. Because probably they'd want that, wouldn't they? Bad teacher. And how many on the O would it need then?
2 times 2. That's all.
What?
2 times 2. Why was it more? No, 2 times 2. Because you have to have the 2.
Right. Okay, hybridization for CO2. Actually gonna be what, Shilpa?
I'm actually not sure.
Okay, Aaron?
is it SB2?
SP2, no, it's, no,
SP,
SPY?
because the double bonds count as single bonds and there's two bonding sites, so it's SP.
Single, double, doesn't matter. It's just how many spots. Good. The shape, I think, Tom, you said it earlier, the shape is.
Linear.
And so now sigma and pi gets a little more interesting. Can remember how to do that for the pi's, for it's a double bond. What do we got to do? 2 people know? Anybody else? Lena, you remember for double bonds what the deal is for sigma and pi?
Was it like a combination of pi and sigma? So
Yeah.
for a double bond, you have 1 sigma, 1 pi.
So I got 2 doubles, so I need
2 sigma, 2 pi.
done. Good. Super. Good job, everybody. Questions about that?
For every pi bond, you need 1 sigma, like.
Yeah.
Okay.
They come together in a 3-dimensional molecular geometry thing that's mainly taught in college. Do I got time for one more? Maybe one more. Let's quickly together do this one. XCF4. I think that'll work. This one is pretty big, isn't it? So let's do XE has how many valence electrons? 8. And each F has 7. So 4 times 7. So got 36. Let's put it in.
I could go to third grade and ace it.
You're gonna ace the time.
Oh, yeah.
Good. So take away 8 from the bonds. And so I got 28. And I'll put how many around the F's?
6.
So all together. What do I do with the last 4? No B.
You put them around the X here because it's one of the atoms that.
Yeah, you got it. So it's an expanded octet. Expanded octet. And let's do the geometry. That's why I actually picked it. So I've got 6 things around 1. So it's like this. with the XE in the middle, except two of those things are, and what do I do with them, Nordi?
I would say it's a square, because they go at the top and the bottom.
That's right.
Square.
So we call it square.
Plane.
Okay.
Thank you very much. See, you guys are tops. Square planar. Jump on.
Does it matter where you put the two loafers around the zone?
It does in this case because not over here, but it does if I think about it here, just to figure out the geometry. They take the spots here to have the most
But for the
elbow
little
room.
stop stuff, we can put it
No,
anywhere else.
that's correct. Anywhere's fine. Noah?
When they ask about bond angles,
Yeah.
they're always talking about angles between the central atom and.
You got it. So what would be the bond angle here, folks?
90 degrees.
90. Good. The bond angle here would be 100 and.
80.
Importantly, what about here?
109.5.
You're right. Tetrahedral angle. Good. Swallow Rooney, my people.